Hello everyone, welcome to the Introduction to Derivatives. In this section, we will learn how to find an instantaneous rate of change. Prior to this point, you've only learned how to find an average between 2 points. Today, we will learn the derivative definition through an example. Now, what I just said here is that we've only learned how to find the rate of change between 2 points, and what I mean by that is we've only looked at the rate of change of a linear function. In other words, we've gone over a certain amount and gone up a certain amount, and we've looked at the rise over the run to determine what the rate of change of that particular linear function is. What we've never done is looked at something like a parabola and figured out the rate of change of that parabola. And we're going to learn how to find the rate of change of something that's not constant today. So let's go ahead and get started with an example. We have a ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is equal to t to the power 2. So the distance is represented by this function s of t equals t squared. Let's graph the function with these certain time values. The first one, we have a 0, and so we plug in 0 into the t spot, and we have a 0. When x is 0, y is 0. Or I should say when t is 0, the distance is 0. And we plug in a 1, 1 to the power of 2 is 1. We plug in a 2, 2 to the power of 2 is 4. We plug in a 3, 3 to the power of 2 is 9, and then we plug in a 4. 4 to the power of 2 is 16. And we can see here that this is a rate of change that's not constant. At 1, we're going a different rate than we are when we're at 4 seconds. We can see that the ball is increasing in speed as the seconds go on. And think about that. If you put a ball on the top of a hill and it rolls down the hill, it will pick up speed and go faster and faster and faster as it rolls down the hill. So this is not constant. So I'd like to figure out what is the instantaneous velocity right at 3. What is the rate of change right at 3 seconds? Now velocity is equal to feet per second, which is the rate of change, which is literally the slope of the function. So we're going to look at the change in feet over the change in time. Now that triangle there in front of the s and the t simply means change. And to find the rate of change, we're going to go back to the good old formula that we have always used, the difference in the vertical values over the difference in the horizontal values. And if we were to do that with just a single point at 3, we would come up with a problem, because we would subtract the 3's down below, and we would end up with division by 0, which is impossible. So we have this problem when we try and find the instantaneous rate of change at a single point, and that's the division by 0 problem. How do we get around that? And that's why this derivative definition exists, because we're trying to figure out the instantaneous rate of change at a single point. So up until now, when we have found the slope, we have used 2 separate points on a line. We figured out the average between the 2 points. Now we're looking for a single point. We come to a problem. Division by 0 is impossible. Let's see how close we can come to finding the instantaneous velocity by finding the average between 2 points. So we're going to use these time intervals from 3 to 4 seconds, from 3 to 3.5 seconds, from 3 to 3.1 seconds, from 3 to 3.05 seconds, and just see what happens as we get closer and closer and closer to that single point. So let's first look at the average rate of change between 3 and 4 seconds. So we go over here, and this represents 3 and 4 seconds here. And so I want to figure out what's the rate of change between these 2 points here. And literally it's this line that goes through these 2 points. And this line here as we see from the previous slide, this line has a rate of change of 7. We have a rate of change of 7. But we could get a better idea of what the rate of change is at 3. So we get even closer, and then we jump to 3 and 3.5. Let's try and get closer to 3 to see what the rate of change is right at 3. And so instead of 3 and 4, we're going to go to 3 and 3.5, and we want to figure out the rate of change in between those 2 points. And so we draw a line between those 2 points, and this line here represents the rate of change in between 3 and 3.5, and we're like, no, we could get even closer. Let's go ahead and try something else. Let's try 3 and 3.1. So we get even closer, really close to 3, and we draw our line here, and we could get even closer, and we see that our rate of change is getting closer and closer and closer and closer to 6. It looks like we're approaching 6. And, we see that our average is getting closer to 6 there, but we don't want to get the average. We want to see what it is at a single point. So we're going to use what we're working with right now and try and come up with a definition that describes how to find the instantaneous rate of change. That's what we're working towards right now. But let's talk about these lines here. These are known as secant lines. Secant lines are the average between 2 points. And what we want to find is the slope of a tangent line, which is actually the rate of change that only touches the graph at 1 point. So we want to see what happens as we get closer and closer and closer to 3. So let's try and generalize the pattern that we've been looking at here. What I've done here is I've rewritten the slopes, the rate of change, so that the 4 is not just a 4. The 4 is represented as 3 plus 1. I'm showing how far away from 3 we actually are. We're plus 1 away from 3. And then 3.5, we're actually plus 0.5 away from 3. And then here at 0.1, we're actually 3.1, we're 0.1 away from 3, and then right here we're at 0.05 away from 3. So I rewrote the slopes as a little bit differently. We're looking for the rate of change right at 3, and so I wrote the slopes with how far away we are from 3. So let's go ahead and try and generalize what's going on here. Let's call 3 that rate of change that we're looking for. Let's call that our time value, okay? And let's call the distance we are away from 3 an h value, okay? So each time we're going to place a t in the 3 spot, and the distance we are away from 3, we're going to call that the h value. So I would say here that if I was going to generalize this overall pattern, I would say that this is a t plus h squared minus t squared over t plus h minus t. So this is a generalization of our pattern so far. Okay, let's generalize even further. We know that the function is s of t equals t squared. So I could say that in minus t squared, I could say a minus s of t instead. And in this spot here, we could say that spot corresponds to s of t plus h. And down below here we have the t minus t, so we could just write an h down below. So this is a generalization of our pattern, and what we're looking for is the rate of change right at 3. And so we were looking at what happens as we get closer and closer and closer to 3. So essentially we were looking at what happens as that h value gets closer and closer to 0. Remember that h value is the distance we are away from 3. So we're looking literally at a limit as h goes to 0. So a lot of times books will use f and x instead. And so this is our definition here. We have to let y equals f of x denote a function f, and the derivative of f at x is denoted by f prime of x. So that little apostrophe there is known as the prime, the derivative. And that's equal to the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So let's get some experience using this particular derivative. I'd like to figure out the exact derivative right at 3 using the function that we were dealing with. S of t equals t to the power of 2. So, well, actually, our derivative right here, I copied and pasted the definition with f and x, but we can pretend for a second that we're looking for the derivative when s is in the place of f and the t value is in the place of the 3 there. So let's get this set up first, okay? We have s prime of 3 is equal to the limit as h goes to 0 of s of 3 plus h minus s of 3, all divided by h. So let's plug in. What we want to do from here is we want to plug in 3 plus h into our t spot, and we want to plug in 3 into our t spot as well. Let's see what that looks like. Okay, so I've plugged in, and from here it's a matter of the algebra skills to figure out this limit. And first thing I want to deal with is the 3 plus h squared. That means 3 plus h times 3 plus h, which means 9 plus 6h plus h squared. So we have 9 plus 6h plus h squared minus 9 all over h. And we're looking for what this is equal to as the limit of h goes to 0. Let's go ahead and simplify some things here. The 9's will cross each other off. 9 minus 9 crosses off. And I'm going to pause and erase some things, and we'll simplify from there. Okay, so we have the limit as h goes to 0 of 6h plus h squared over h. And we can simplify that. We could actually factor out an h from the numerator, and that gives us h times h 6 plus h, and we can cross off an h in the numerator and denominator, and we are left with the limit as h goes to 0 of 6 plus h. And there's nothing that we can do from here, and so we plug in h equals 0, and we have 6 plus 0, and that gives us a 0. And so that means that s prime of 3 is equal to 6. In other words, the rate of change right at 3 is equal to 6. If we go back to that picture right here, that would mean that the slope of the tangent line right at this particular point is equal to 3. In other words, for every one that we go over, we go up 6. And that is the rate of change of our particular function for this one here at 3. I will continue on in another link in a sec. Okay, so let's get some more practice here finding the derivative. We're going to use the function f of x equals x squared to find the slope of the tangent line at 1 and at -2. Let's go ahead and start off with 1. We have f prime of 1. So in the x spot, we have a 1. So we have the limit as h goes to 0 of, we have f of 1 plus h minus f of 1 all divided by h. Okay, so we need to plug in some values into the x within our function. Let's see what that looks like. Alrighty, we've plugged in our values and we have this algebraic expression that we need to deal with. And we have the limit as h goes to 0 of, we have 1 plus h squared. That literally means 1 plus 2h plus h squared, and then minus 1 to the power 2, which is just 1. So let's see what we can do at this point. We have a 1 and a minus 1, which we can get rid of. And now we have a left, we have a 2 plus h, 2h plus h squared, all over h. So I'm going to do a couple steps at once. I'm going to factor out an h from the numerator here. So we have h times 2 plus h, and this is all over h. So I got rid of the 1s and I factored out an h, and we see now at this point here we can cross off these two h's. And so what we're left with at this point is the limit as h goes to 0 of 2 plus h. And there's nothing we can do here to simplify except plug in h equals 0, and we see that the slope of our tangent line right at 1 is equal to 2. What the heck does that mean? Let's get a visual of what's going on here. What I need to do is graph f of x equals x squared. So I'm going to go ahead and graph this. Okay, so here we want to understand what f prime of 1 really means, what f prime of 1 equal to really means. And so we go to our function, f of x equals x squared, and we go to that point 1. We go to 1, and we know the slope tells us to go up 2 and then over 1. Now, we could also go down 2 and over 1 to come up with another point that's on that line. So the slope of our tangent line that just grazes our point right at 1 is equal to 2. That means the rate of change right there at 1 is equal to a 2. We can see here that as the x values increase, the rate of change gets steeper and steeper and steeper. The line becomes more and more steep there. Now the previous problem, it said also to find the equation of the tangent line right at 1. Well, what that means is we're looking for y equals mx plus b. So what is the equation of our tangent line? Well, we know that the slope of the tangent line is 2. What is the b value? We could just eyeball it right now and say, oh, yeah, well, that's equal to a -1. But if we wanted to know exactly how to find it algebraically, we would need to plug in an xy point and solve for b. What is an xy point that's on our line? Well, right here. When x is 1, we plug that in, we have 1 power 1, which is equal to a 1. So we plug in that point when x is 1, y is 1. And we solve for b. And that gives us a b value of -1. And so we end up with y equals 2x minus 1 for the equation of our tangent line. So today we're going to find the derivative of an actual function, x squared. To give you some backup here, where we came from, we did find derivatives of we found the slope of a tangent line at specific points on x squared, and we can also, though, find the actual derivative of the function itself and then simply plug in the x value where we want to find the slope and find the slope that way. So if you're going to be finding the slope of a tangent line at multiple points for a particular function, it might be best to just find the derivative of the function and then from that point plug in specific x values to find the derivative at those particular points. So let's go ahead and start this one off. Okay, so all I've done at this point is I've plugged in x plus h into the function here, into x, and I've subtracted the function itself. So I've just plugged in using the definition. From here, I need to expand x plus h squared and multiply. So I've expanded and multiplied x plus h squared. And now I have the ability to cross some things off here. And let's see what we get. Okay, so here's the simplified form, but we can simplify further by factoring out an h in the numerator. Alright, so I factored out an h, and that gives me the ability to cross off two h values. This eliminates the division by zero problem. And so now at this point, there's nothing else we can do to simplify, and so we can simply just plug in h equals 0. And see that our derivative for x squared, f prime of x, is equal to 2x. Let me put this in context for you. Yesterday, we found the derivative at -2 and at +1 for x squared. And today we're finding that the derivative of that function x squared is equal to just 2x. So if I wanted to just use this derivative here to find the slope of the tangent line at -2 and at +1, I would just simply plug in to my derivative function. And so if I plug in a 1, I have a 2 times 1, which gives me a 2. That should make lots of sense. That's what we found yesterday. So I could do that with -2 as well. So I have a -2 plugging in, and I end up with a -4, which once again should make lots of sense because that's what we found yesterday. You guys have any questions on that? Okay, so we're going to go back and figure out the derivative of a function at a specific point. We're going to find f prime of 4, but now the function's a little bit more complex. So let's go ahead and get the setup and work it from there. Okay, so here's the setup, just according to the definition I've highlighted to help you understand the flow. And so from here, it's really just a problem that deals with your algebra skills. We have to expand and multiply, use the order of operations, and I'll go ahead and pause it and show you the next step. Okay, so here is our next step. After I've done some simplification, I need to continue to see how to simplify this problem, and I'm going to pause it once again. Okay, so now I've simplified here, and I see that I can cross off these 32's, plus 32 minus 32. And I'm going to be able to factor out an h in the numerator there and cross off the h in the denominator, which is going to eliminate that division by zero problem. Let's see what that looks like. Okay, so here we are at the limit of h going to 0 of 16 plus 2h, and there's only one thing that we can do. Plug in h is 0. So we end up with 16 plus 2 times 0, which just gives us a 16. In other words, f prime of 4 is equal to 16. And what that means is the slope of the tangent line at 4 on our graph is equal to 16. Alright? It doesn't ask for it, but I kind of want to show you guys the visual of what's going on there. So I'd like to figure out the equation of the tangent line and make sure that that really does go through just touching the graph at one point. I'll show you what I mean. To visualize this using the calculator, I need to figure out the equation of the tangent line that grazes right at 4. And that means that I need to figure out y equals mx plus b. I have the slope. That's equal to 16. I need to figure out the b value. And so I need to plug in an x, y value that is actually on our graph. So when we plug in 4 on our graph, we end up with a y value of 29. So I'm going to use when y is 29 and x is 4 to figure out the b value. So I plugged in my point and I ended up with a b value of negative 35, which means that the slope, the equation of the tangent line at 4 on our graph is equal to 16x minus 35. Let's get a visual of what is going on here. So to check my work, I've plugged in the function itself, f of x, into the first y spot, and I plugged in the equation of the tangent line into the second y spot. So if I hit graph here, I have my parabola and then I have my tangent line there. It looks like I'm on the right track because it looks like we're just going to graze the graph at 4. If I want to specifically see where we do touch, I'm going to have to change my window. So I'm going to want to change my y values in the max part. So let's go, I don't know, say go to 40. Might be way too much, and I'm going to scale by 5. Let's see what that looks like. There's our graph, and there is the equation of the tangent line. It should be just grazing right at 4. It's kind of hard to see, but I think we're right. Okay, last one. What we're looking for here is dy over dx, and what that means is the change in y over the change in x. That's literally asking for the derivative. Okay, so this is just another way of them telling us to find the derivative. Dy over dx means change in y over change in x, which is the rate of change, is slope, right? So we want to figure out the derivative of a particular function, y equals 1 over x. So we set up the same way. It's just now we're using dy over dx, and the limit sh goes to 0. I'll go ahead and get the setup first. Alright, so here's our setup, and at this point it's just an algebraic problem. You got to be good with your algebra skills. How do you simplify that expression? What do? You need a common denominator. First of all, I'm going to go ahead and give that one the negative so I don't forget about distributing a negative, and I need a common denominator. So I ask myself, what is the left side missing that the right side has? Missing an x. What is the right side missing that the left side has? An x plus h. And so I'm going to deal with everything above our h here, and I'll pause it and see what happens. Okay, so I've gotten a common denominator and combine those numerators, and I see that I can cross some things off here. I have an x minus x, that's going to cross, and now I am left with a division with fractions problem, and so I'm going to have to invert and multiply. So I have this entire quantity in the numerator divided by h. So I'm going to multiply by 1 over h. We're dividing by h over 1, so we're going to multiply by 1 over h. I'll show you guys the next step. So inverting and multiplying gives us the ability to cross off some h values. And now we are left with the limit as h goes to 0 of negative 1 over x times x plus h. And what can we do to simplify from here? Really nothing except plug in the h value of 0. So if we plug in h equals 0, now we have a minus 1 over x times x plus 0, which is just like saying negative 1 over x squared, which is what dy over dx is equal to. So if I want to figure out the slope of the tangent line at any point on our original function, I simply plug in to our derivative function to figure out the slope of the tangent line. Any questions there? Thanks for joining us. Stop dancing, Hassan. I know. Okay, welcome to our extra fun example problem. I am video recording this one. Yes.
Everybody.
Start over.
No, we'll go ahead and capture that. All right, so we're going to find the derivative. We're going to find the derivative of f of x equals the square root of x. So let's go ahead and start plugging away here. We have f prime equals the limit as h goes to 0 of, we have the square root of x plus h, minus the square root of x all over h. And you're like, let's see here. What could I possibly do? What the heck is going on here? What could I do to simplify this problem? There's not really a whole lot you can do except you can do something called rationalize the numerator. You see, I'm trying to get rid of my division by 0 problem. And I can accomplish that goal by rationalizing my numerator. So I am multiplying by the conjugate of the numerator. Okay? Okay, so we need to multiply. And we have, essentially up top here, we have like a difference of squares, right? When you multiply a difference of squares, essentially you just multiply the front and the back, right? You guys remember that? Should I refresh your memories real quick here? Yes, real quick. X minus 5 times x plus 5. You know, if we multiplied that whole thing out, we'd end up with x squared plus 5x minus 5x minus 25. And so we just end up with x squared minus 25. And so what I'm saying here is when we have a difference of squares, we could just not even really think about that middle part and multiply the front and multiply the back, right? So that's what I want to do right here. I just want to multiply the front and the back, okay? And so we have the square root of x plus h times the square root of x plus h, which is going to give us just x plus h. And then we have to multiply the back there, which is going to give us a minus x. And this is all over h times the square root of x plus h plus the square root of x. And at this point here we have a minus x and a plus x. These guys cross each other off. And lo and behold, by rationalizing the numerator, we end up being able to cross off some h's, which gets rid of our division by 0 problem. All right? So we have the limit sh goes to 0 of 1 over square root of x plus h plus the square root of x, and there's nothing else we can do here except to just plug in h equals 0, and so we end up with, we have a 1 over the square root of x plus 0, which is just the square root of x plus the square root of x, and these are like terms, and so we can combine them, and we can write a 1 over 2 root x. And that is the derivative of that particular function. And if we want to get really fancy here, you know what we could do? We could rationalize the denominator if we wanted to. Yeah, and so if we wanted to get really fancy, we could say, let's rationalize the denominator. And that's going to give us root x over 2x, right? But, you know, I think this is perfectly acceptable. Do you guys want to do one more? Or?
Do you feel ridiculous when you talk to yourself on these when you're like alone in the classroom? Like when you're just like talking to, he's like talking to himself on the phone when
How do
there's
you
no
know
one
there's
else
not
in here.
someone there?
Because well, I listened to that by choice. I don't know.
That's
I
just-
don't know. I was assuming.
Every single document today.